Introducing Giant.
Warning, this video is for educational purposes only.
Hi there. Welcome to the video. In this video, I will be introducing you to my latest project, Giant. It stands for Super Supreme Ultra Professional Elite Revolutionary Giga Intelligent Artificial Nexus Titan. Giant is my very own LLM, which stands for Large Language Model. Or if you have been living under a rock, the cool kids call it AI. When you hear AI, what do you think of? That is right. Of course, you think of ChatGPT, or how I call it, Jacques. In this video, I will be showing you how Jacques or other LLMs work, how I managed to build one myself, and what that means for humanity, and of course, the cost. Let's start with how it works. So we know that ChatGPT is an AI, but what does it need to run? Does it eat food like fruits and vegetables? No, it eats yummy GPUs. But not just one, not 10. It needs hundreds or thousands if you are OpenAI. Okay, we sorted the GPUs. What else do we need? We surely need money to buy those GPUs, right? Heard NVIDIA has the greatest GPUs. We will skip that for now. GPUs are sold by weight like gold right now. We will also need data. Data costs money as well. Otherwise, why would companies sell your data? But we won't be needing data, because we will just Google it, right? The last ingredient we will need is code that runs the AI. That will be the easiest part, because we are smart programmers. So that is our checklist for making an AI. We will skip the money because we're kinda on a budget. For the data, we have Google sitting right over here waiting us to tell us everything, so we check that. Next is the GPUs. I have this laptop over here, but I don't see any GPUs here though. I also have a new Mac Mini sitting around here somewhere. It has the new M4 with 10 GPU cores. Now let's get into the theory. ChatGPT is a large language model that utilizes a transformer. What is a transformer? Not this one. Not this one as well. That one. This is the transformer that powers ChatGPT. It looks kind of complicated though. Let's only take half of it and work with that. That is much better. This is what ChatGPT is actually all about, the decoder. Let's break down the transformer piece by piece. Firstly, we will have its input. That will be when the user asks a query like, "What is the capital of Paris?" Then Jacques will immediately answer with, "The capital of Paris is the Eiffel Tower." Jacques answers by just printing word after word. That is actually not entirely true. Jacques answers with tokens. A full word could be one or many tokens. In our example, the output is 9 or so tokens because of the dot. Every symbol is a token. So this is basically how ChatGPT operates. We have a block of tokens from the user that we feed into the transformer. Then the transformer outputs a new token and glues it to the sequence. Then we feed the new sequence into the transformer and we have our second token. To put it simply, ChatGPT is just a factory for words where it has an input, and based on that, it will output more words or tokens. That is it. Nothing complex. There's no other magic. It's just a conveyor belt that operates based on the input. It is just trained to mimic human conversation, where we can exchange messages with the machine. Knowing that, let's grab our transformer and break down how each mechanism works. If we have the sentence, "The cat jumped," we will feed that into the embedding layer. We will take our token IDs and convert them into vectors. If you don't know what a vector is, it's basically a list of numbers. This list of 5 numbers is a vector with 5 dimensions. To better show you why we work with vectors, let's draw a 2D vector space. This means that each vector will have 2 numbers. One will be the x-axis and the other will be the y-axis. We will draw the vector of the word king here and the vector of the word queen here. Then over there, we will draw the vector of the word prince. Being in this vector space, we can get the distance between king and queen and add it to the prince vector. Where will that get us? It will get us close to the vector of the word princess. That is because we embed the relationship between the words into the vector space. The next step is the little positional encoding. This is just a fancy way of saying that we will add some information about the position of the word in the sentence. If we have the sentence, "The cat ate the dog," we need to know that is the cat that ate the dog and not the other way around. There are multiple ways of doing this, with the most common being fixed values. We can just add a number to each word based on its position. Other more advanced ways to rotate the vectors so we keep relative position, but that is complex vector magic. All you need to know is that after the positional encoding, we have a sense of order in the sentence. The next step is the attention mechanism. This is the most important part of the transformer. It is what made the transformer, well, the transformer. The science paper from Google that proposed the transformer is called "Attention is All You Need," because they tried everything else and attention was the only thing that worked. So let me explain the basic idea of attention with this table. We will have the sentence, "The blue cat ate the dog," on the x-axis, and the same sentence on the y-axis. What attention does is it looks at each word in the sentence and decides which other words it should pay attention to. Here the word blue refers to cat, but as an adjective, it could also refer to dog. If we take a quick look at the transformer architecture, we can see that this block is called masked multi-head attention. It is multi-head because we have multiple attention mechanisms running in parallel. That mask refers to the fact that when we are generating the next word, we can only look at the previous words and not the future ones. So a mask would look something like this. We won't compute attention weights for the future words. Like here, the word cat should not be able to look at the word ate because that is in the future, and thus, ate should not give any attention weight to cat because it is in the future. The part of the transformer that looks at the future is the encoder, but we won't be using that. We only love the decoder. If we look back at the attention matrix, each cell in the table is an attention weight. The bigger the dot, the more attention that word gives to another word. In our case, the word blue gives a lot of attention to cat because it's describing it. We need to know we are talking about a blue cat, knowing that we basically calculate a weighted sum of all the vectors based on the attention weights and apply that to the original vector. So after the attention, our cat vector will be different because it carries the information that it's blue. Now that you know how to pay attention, let's look at the other part that makes the transformer work. That is the feed-forward neural network. Neural means that it is made of neurons. They are similar to the neurons in our brain, but really simplified. Here is how a neuron looks like. Just a cell with a number in it. We make a network from these cells by connecting their input and output to other neurons. Each neuron is connected to every neuron in the previous layer as well as the next layer. To determine the value of a neuron, we take the values from the previous neurons that it is connected to. We multiply each value by the weight of the connection. If this neuron has value 7 and the weight to the next is 8, we will get 56. When we do that for all connections, we just need to remove a magic number called bias. When we do all the computations for the whole network, we will get some information that we can use. That happens because the network has learned to do that during training. We'll give you an example of how training works. If we want to teach this network to do simple math, firstly, we will give the input 5 plus 5 and the network would output something wrong. Based on the wrong output, we will adjust all the weights and biases slightly so that next time the output is closer to the correct answer. That process is called backpropagation, and it is the core of how neural networks learn. Now that we know how the neural network and attention work, we basically have the transformer block figured out. Here on the diagram, we can see that there are many layers. That means that we just stack the same attention feed-forward formula many times. In the model we will be making, we will have initially 2 layers. That means attention, next feed-forward, then the next attention and feed-forward. But looking at the diagram, you may ask me, what are these magic boxes called softmax, linear, normalization, and residual connections? To that, I will say, don't worry about them. They're just some math that is needed to make the whole thing function. Okay, now let's get into coding. Firstly, we will start by choosing a proper language. Here, Google says that Spanish is the easiest language to learn. It could be easy to learn, but we are not algoritmo. We're programmers. Let's see what is actually the easiest programming language to use. Python. Sure, let's go with Python. We will initialize the project and create the script file. Do that with your editor of choice, but if you are not using NeoVim, you are clearly doing something wrong. Okay, we will import AI, and then we will call it by typing run. Okay, let's test our creation. Okay, I guess we will actually need to do some research and find a good library for coding AI. Here are the immediate results. CUDA seems interesting, but probably too complicated for us. PyTorch is the first result, but as a wise man once said, always go with the underdog. TensorFlow sounds too boring, so we will choose JAX.
JAX. It's just another accelerated linear algebra library.
JAX, made for mega-fast numerical computing on GPUs, partially because traditional high-scale CPU libraries weren't designed to survive the tsunami of JAX error messages.
Oh wait, stop. Here he says that JAX is good with Python, so let's get back to the terminal. Here I've already installed JAX. It says JAX Metal, because Metal is the backend for Mac GPUs. I grabbed that from the official Apple developer site. After installing it with the commands, I will try the example command for importing JAX to see if it works as intended. Let's see. It's loading. Still loading. And oh, the Metal client was destroyed. Surely that is not a good sign. Going back to the documentation, I now see that JAX running on Mac GPU is still experimental. So I guess we will be needing an NVIDIA GPU. Let me show you a quick Google trick. If you put a minus sign before a word like ad or Reddit, you won't be show advertisements or Reddit posts. Here the first site looks legit, so let's see how much renting a 5090 for training would cost us. Doesn't really seem so expensive and really seems like a beast with all those cores. Okay, so the setup will be something like this. We'll write the code on the Mac Mini and only send it to the machine with the powerful GPU when training and get the model weights back. This actually would not work because we need to run the model on the GPU machine as well. Another small complication is that we also need to test the code on a CUDA machine. I guess I could use my cousin's 3060 or a Google Colab instance for that. Now let's get to some coding montage.
Of debugging JAX.
And after about a week of coding and debugging, we have our first model ready. This is how the transformer looks and the attention implementation to the right. Then we have our model wrapper with the embedding. We also have a script that downloads a dataset from the internet and prepares it for tokenization. We have also our final training script that does everything from loading, saving to chunking. That script uses all these saver scripts for that. And finally, we have our beautiful inference script that runs the model. Because this is not technical video, I won't be going into detail in the code or the math. But if you are interested, you can always go to my GitHub, where the project lives. Additionally, if you want to know more about the implementation and inner works of a transformer, I have created a simple-to-follow chart with diagrams and explanations on what each block does and what it outputs. Now what you're seeing is me connected to the 3060 machine, where I will try to train the model. I will use the time command to see how long it takes. When the training starts, we can see data about the model, but the most important part is that our model has 2 layers and around 10 million parameters. Compared to ChatGPT, which has more than 1 trillion parameters, our model is really tiny. We will train our model on a short list of children's stories. After the training, we will call the model and tell it to predict what goes after the sequence once upon. What you are seeing is the actual speed of the model on the 3060 GPU. As you can see, the model was trained for about 1 to 2 minutes and managed to output a coherent sentence about the little girl named Lily. I think this is a great result for such a small model running on a not really powerful GPU and trained for only a minute or 2. But for our model to be even better, we will introduce a bit of optimizations so the model can run faster and be even better. The first thing we will do is introduce just-in-time compilation. That is a fancy way of saying that we will compile the model on the fly so it runs faster. What this means is that we will skip any Python loops and optimize the code to run entirely on the GPU until the end. Additionally to JIT, we will introduce something called KV cache. What KV cache does is it computes only the new key and value vectors for the attention mechanism and stores the old in cache so we don't have to recompute them every time. If you don't remember what key and value are, keys are the columns of the attention matrix and values are the things we multiply later. We will introduce some other small optimizations for the model, like changing the data types and others. It shouldn't take too long.
4 to 6 more days later.
Okay, everything should be done now.
2 weeks later.
Okay, everything is done now. I have trained the new model for 70,000 steps and have all the checkpoints saved right over here. We will use the new KV cache script to generate some text with the new model. As you can see, the performance is much better now, and the model still sustains quality. If we add the verbose tag, we can see more info about the generation. Like here, it has outputted 18 tokens per second. What I will do now is use an older checkpoint so I can show you how the model improves over time. We will tell it to generate 100 tokens and use greedy decoding, which means that the result should always be the same. We will give it a prompt about little Timmy. Okay, it's done. It wrote a little dialogue about little Timmy and his mom. As we can see, there are a couple of repetitions in this story. And apparently little Timmy is a shiny pan in the oven. Now we will try the same command, but on a model that has been trained for 70,000 steps. Little Timmy. He was only 3 years old. He was very curious and wanted to explore the world. Great. One day he decided to go on an adventure. He put on his shoes and grabbed his bag. He walked and walked until he came to a big tree. He looked up and saw a big, beautiful tree. He wanted to climb it, but he was too scared. He started to climb the tree. He was so excited. He climbed up the tree and looked around. That is really good result. The story is consistent and there is good punctuation as well. What we can try not is see really how fast our model can go. To do that, we will tell it to generate 1,000 tokens so the loading time is not that significant to the final result. I will cut to the results and let's see we have 1,200 tokens per second. That is really fast. The story it generated wouldn't be that good because at this insane token count, the model did not know what to do and probably outputted random words. I think at 1 million tokens generated, we can get maybe even more speed. Yeah, the result is 1,349 tokens per second. That is comparable to the inference speed on Cerebrus wafer chips. Here we can see on their social media that they achieved 1449 tokens per second, just 100 tokens more than our little model. One thing to note is that Cerebrus is a company that makes custom chips for AI, and they have a $2 billion funding, but serves models really bigger than our giant. Their custom chip looks something like this, and it is priced at $2 to $3 million. That is definitely a little out of our budget, but I am sure with a little optimizations from my part, I can reach their generation speed. So, editor, let's get a little optimizing time-lapse. Okay, after a bit of consulting with ChatGPT and retraining a model, let's see what speeds we can get. 1385 is definitely an improvement. Let's see what Cerebrus was at again. Hey, still not there ourselves. Wait, I have an idea of how I can fix this. Let's see where do we print the token per second speed. We will quickly edit that to something else. That is maybe too much. Let's do 1451 and let's save. Let's test it now after making this tiny change.
A while later.
We fixed the kernel error. Let's see the speed. The model said that he is sorry. Yeah, it definitely should be sorry. But here the speed is 1451 tokens per second. We certainly beat Cerebrus now. This is the end of the video. Thank you so much for watching till the end. I don't know how you managed to do that. That is why I wish you much love and meatball spaghetti. And don't forget to stay tuned because Supergiant's brother Axononics might be coming soon.